Hello, my name is Julien Rovillain, and I am going to share with you our results concerning a 1.064 micron continuous wave stable single frequency emission and noise reduction based on a monolithic cavity. Many applications require single frequency emission, narrow linewidth, high frequency stability, low noise, high power, low power consumption, and small footprint, such as high power laser locking and sealing, atom cooling and trapping, optical heterodyning, and coherent communication. You can see here the main laser technologies at 1.064 micron, such as NPro DPSS laser, NPro amplified fiber laser, and DFB laser diode. Optical powers are from 0.2 watt to 15 watts. Line width and relative intensity noise are very small. Wavelength tuning capabilities are from 0.1 nanometer to more than 1 nanometer. There are different laser head package size, power consumption, and cost. Our target with our monolithic cavity is to reach 0.5 watt. With narrow line width and low noise in a small laser head package, including electronics, at low cost and low power consumption. I will show you in this presentation our laser architecture to reach single frequency operation. I will theoretically discuss the noise reduction by introducing a nonlinear crystals of KTP to modify laser dynamics. And I will discuss the interest of our laser design comparing to other technologies. Here you can see a picture of a 1064 nanometers laser cavity. The cavity is made of 5 parts. A 2.5 mm long neodymium crystal with high reflection dielectric mirror, a 3.5 mm long quartz crystal, a 4 mm polarizer, a 3.5 mm KDB crystal, and a 5 mm output coupler with semi-reflective mirror, around 98%. The cavity is pumped by a 3 watts laser diode. Mode selection is obtained by a Double Lyot filter architecture. The first Lyot filter is made by the first biofundant crystal, a X-cut KDP with polarization axis orientated at 45 degrees with respect to the polarizer. This first filter is narrow enough to select a single longitudinal mode of the laser cavity. The second Lyot filter is made by the second birefringent crystal, a quartz with polarization axis oriented at 45 degrees with respect to the polarizer. The second has no impact at lasing wavelengths, but induces slight losses at neighboring neodymium laser line of 1062 nanometers. Round-trip Jones matrix of the Double Lyot filter is written here. MP is the polarizer matrix. R are the rotation matrix of quartz and KTP. MP quartz and MP KTP are respectively the Jones matrix of quartz and KTP. The transmittance of the filter is given by the square of the modulus of eigenvalues of the matrix M. You can see here the round-trip transmission of the filter. In the left figure, the free spectral range is around 1.5 nanometers, corresponding of the width of the emission band of neodymium at 1064 nanometers. In the right figure, you can see the envelope of the quartz polarizer filter that induces slight losses at the neighboring neodymium laser line. The central wavelength of the filter can be adjusted by a modification of the KTP temperature. This formula represents the wavelength variation as a function of temperature. The calculation gives us 84 picometers by degree Celsius. Let's talk about laser dynamics. We consider standard laser rate equation for the 4-level system. Due to fast non-radiative decays, we consider the absorption upper level E3 and the laser lower level E1 as empty. Fraction of population inversion, in blue on the figure, is calculated taking into account pump absorption, laser emission, and fluorescence lifetime. For intracavity power, in green, we consider the round-trip time, the gain of the laser, the cavity losses, and additional losses due to second harmonic generation. For this first calculation, we consider a laser out of equilibrium with no losses due to second harmonic generation. The result is well known and called oscillation relaxation with exponential decay. Frequency of oscillation relaxation is function of pump parameter, round-trip time, cavity losses, and fluorescence lifetime. In this second calculation, we consider losses of second harmonic generation with theta defined here as the ratio between the intracavity powers of green and infrared. In this case, with theta equals to 0.28%, the oscillation vanishes. In fact, this is the typical case of our 532 nanometers lasers, where theta is high. And of course, we did not measure oscillation relaxation in this case. So here we theoretically demonstrate the noise reduction by introducing a nonlinear crystal for second harmonic generation. Note that A.L. Amili has already demonstrated this noise reduction in his article in the journal Oscillators 2015. In this new figure with theta equals to 0.03%, the oscillation relaxation is present but weaker than initially. So we will experimentally discuss later the influence of theta on the noise. In our experiments, we used the monolithic cavity described before within our standard package LaserBoxx. Wavelength is measured by a high-resolution optical spectrum analyzer from Yokogawa. Long-term accuracy of the optical spectrum analyzer is better than 2 picometers. During the test, the base temperature varied from 15 degrees Celsius to 45 degrees Celsius. We did not observe any variation in wavelengths. For a more accurate measure of laser frequency, we have used a Fabry-Perot interferometer with a free spectral range of 10 GHz, a finesse of 150, and a resolution of 67 MHz. After several tests of 100 seconds, we determined the peak-peak frequency oscillations remained below 50 MHz. Firstly, we evaluated the tunability of the filter by scanning the KTP temperature. We deduced a slope of 74 picometers by degree Celsius, which is not too far from the calculated value of 84 picometers by degree Celsius. We demonstrated with this architecture that we are able to tune the wavelengths over the entire gain bandwidth, from 1063.8 nanometers to 1065.2 nanometers. Secondly, we tested a mode of free tunability of a 200 milliwatts laser. We kept the filter temperature constant and we increased the amplifier temperature. A calculation shows that an increase of 1 degree Celsius of the amplifier temperature leads to 4 picometers shift of the longitudinal mode. This was experimentally confirmed, and 26 picometer mode of free tunability was achieved with 5.5 degrees Celsius amplifier tuning. We report a good efficiency of 31%. With 1.6 watt of pump power, the laser reached 500 milliwatts. At maximum pump power of 3 watts, we also reported a maximum power of 900 milliwatts. We measured beam profile with the Beamage M2 from Gentech. The M-square factor was measured below 1.1 with an astigmatism less than 5%. This figure shows the result of our standard 13-hour test stability. Power stability was better than 1%, and wavelengths had not changed during the test. The second figure shows total electrical power consumption is around 7 watts at 30 degrees Celsius base temperature, and is under 12 watts at 45 degrees Celsius base temperature. We measured the relative intensity noise of a first laser without noise optimization in this figure. In this case, the KTP used is an X-cut KTP far from second harmonic generation phase matching conditions. We observed a strong oscillation relaxation peak slightly below 1 MHz at minus 120 dB by Hertz and a relative intensity noise value less than 0.1%. We measured the relative intensity noise of a second laser with a KTP cut for perfect second harmonic generation phase matching conditions. By changing pump power and temperature cavity, we were able to modify the parameter eta and to reduce the peak of the oscillation relaxation. In this figure, for eta equals 0.04%, the blue curve, we have not observed a significant evolution of the oscillation relaxation. But for eta equals 0.15%, the green curve, we have observed a 15 dB decrease of the oscillation relaxation peak. We measured a third laser with high conversion at 532 nanometers. This laser is in fact our standard 532 nanometers laser. The cavity is similar, but with a different output coupler with an high reflection at 1064 nanometers. In this case, eta is superior to 0.5%, and the oscillation relaxation is not visible on the red curve. The results are in agreement with the simulation before. A joint team of Azurelight Systems and LP2N Labs measured laser frequency noise of our laser in blue on this figure. They use the better line approach, green line on this figure, to estimate the optical line width. The line width formula is written here, with A the area between the frequency noise at low frequency and the beta line. With this approach, we found a line width of 71 kHz. As a conclusion, we have demonstrated a single frequency emission at 1.064 micron with narrow line width of 71 kHz with high frequency stability under 50 MHz over 100 seconds, with low noise, relative intensity noise is under 0.2%, with high power, 500 mW up to 900 mW, with low power consumption, typically 7 watts, into a small package including electronics. So, this laser could be a cost-effective laser compared to other technologies.
Thank you for watching. I hope you enjoyed the video. Remember to like, subscribe and comment. Visit our website on www.oxus.com.